Welcome to your lesson 6.2 business calculus lesson. Today we're going to look at antiderivatives again and more Reimann sums. Okay, when finding the area under a curve by adding the rectangles, the answer is called a Reimann sum. We did that last time. The width of the rectangle is called a subinterval. So if we're talking about, well, what is a subinterval? We're talking about the width of a rectangle. The entire interval is called the partition. Subintervals do not all have to be the same size. If the partition is denoted by P, then the length of the longest subinterval is called the norm of P and is denoted by the symbol you see right there. As the norm of P gets smaller, the approximation for the area gets better. That makes sense. We talked about if there's more rectangles, the approximation gets better. So if there's going to be more rectangles, it makes sense that the norm of P would get smaller. All right. So the area under this curve is going to be the limit as the norm of P goes to 0. As K equals 1 to n, we're going to take the sum of f of the kth constant times delta x for whichever value we have. So for the kth number. If P is a partition of the interval A to be inclusive. So this value is called the definite integral of f over a b inclusive. If we use subintervals of equal length, then the length of a subinterval is delta x equal to b minus a over n. The definite integral is then given by the limit as n goes to infinity for k equals 1 to n of the sums of the f of ck times delta x. Leibniz introduced a similar notation for the definite integral, which is what we're used to, what we typically see. Another way of expressing what we just talked about is the integral from a to b of f of x dx. Note that the very small change in x becomes dx, goes from delta x to dx. So this is the integration symbol. A is the lower limit of integration. B is the upper limit of integration. And since this is in terms of x, those would be x values. F of x is called the integrand. And dx gives you the variable of integration, the dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. We have the notation for integration, but we still need to learn how to evaluate the integral. That's great that we can, write it out, but how do we go about evaluating? All right, so we're going to go through some kind of background information, and then we're going to do some algebraic geometric manipulation to show you why our method of evaluation is going to work. So in section 6.1, we considered an object moving at a constant rate of 3 feet per second. Since rate times time equals distance, 3 times t equals d. So 3 times the number of seconds is going to equal the distance. So if we draw a graph of the velocity velocity, the distance the object travels is equal to the area under the line. So after 4 seconds, the object would have traveled 12 feet. But what if the velocity varies, like in this one? The velocity is equal to 1/2 of t plus 1. Okay, so if you look, that's a linear function. And here's our y-intercept of 1. And to get to the next easy point to find, we would go up 1 and over 2. And there you go. We could do up 1 and over 2 again and come to another point on that line. So the distance for this would be s equals 1/4 t squared plus t. C equals 0 since s equals 0 at t equals 0. So this is what our constant is. All right, so after 4 seconds, our distance formula would give us 1/4 times 4 squared, so 16 plus 4, and so we would get the distance equals 8. Okay, so let's look at the area under the curve. So the area under the curve is going to be 1/2 of 1 plus 3 times 4, and that's going to equal 8. Okay, using our nice trapezoid formula for area. So the distance is still equal to the area under the curve. Okay, so even if the velocity varies, that truth is still holds. What if we had a velocity equaling to 1/8 times t squared plus 1? We could split the area under the curve into a lot of thin trapezoids, and each trapezoid would behave like the large one in the previous example. Pretty cool. It seems reasonable that the distance will equal the area under the curve, since we're using the same method that we did previously, and it worked. All right, so our velocity is the change in speed over change in time, ds dt, and that is equal to 1/8 t squared plus 1. So s is going to be, our distance is going to be 1/24 t cubed plus t. And so s is going to equal, in the case of taking it to 4 seconds, it's going to equal 1/24 times 4 cubed, since we're plugging in 4 plus 4. And so we get that the distance is equal to 6 2/3. And the area under the curve is 6 2/3. We can use antiderivatives to find the area under the curve, which is really cool. Let's look at it another way. Let a of x equal the area under the curve from a to x, and a is just some constant. Okay, so this is a of x. Then a of x plus ax of x plus h, okay, the total area right here, is equal to a of x plus h, so the total area from a to x plus h. If we rearrange that, we can get that the area of ax of x plus h, okay, our term right here, is equal to a of x plus h minus a of x. The area of the rectangle drawn under the curve would be less than the actual area under the curve, okay, because there's a little bit left over. A little bit of area we have not accounted for. So here we've got a distance of h on our horizontal axis, and then we have the minimum f value for that curve on the y-axis, the vertical axis. The area of the rectangle shown above the curve would be more than the actual area under the curve. So here, if we take the maximum value of our function, okay, so the maximum function value, and we multiply it by h, that's going to give us this rectangle that has a little bit of extra area. So the short rectangle is actually less than or equal to the area under the curve, which is less than or equal to the tall rectangle. All right, so using our area formula, h times the minimum value of f is equal to this area, AA of x plus h minus AA of x, and that's going to be less than or equal to our h times the maximum of f. Okay, the area of the large rectangle. So this is the true area under the curve, and it's going to be somewhere between the area of the short rectangle and the area of the tall rectangle. So we can divide everything by h. So in the first term, the h cancels. In the middle term, we put the h on the bottom. And then for the the right term, the h cancels. So the minimum function value is going to equal that area, going to be less than or equal to the area under the curve divided by h, and it's going to be less than or equal to the maximum function value. As h gets smaller, a really cool thing happens. The minimum of f and the maximum of f get closer and closer together. Okay, so as we have smaller and smaller distances on the x-axis, we'll have smaller and smaller differences on the y-axis. All right, so a way to write that mathematically is the limit as h goes to 0, this area under the curve over h is equal to f of x. This is the definition of derivative. Very cool. So d dx of the area a of x is equal to f of x. Take the antiderivative of both sides to find the explicit formula for area. Okay, so we're going to take the antiderivative of both sides. So AA of x is the area of a along x is going to equal capital F of x plus c. Okay, this is your antiderivative. The initial value is going to be AA at a, which is equal to f of a plus c. So for our example, 0 equals f of a plus c. So negative f of a is equal to c. And so if we plug in negative f of a for c, we get AA of x is equal to f of x minus f of a. So the area under the curve from a to x, that's what this is, area AA of x is area under the curve from a to x, is equal to the antiderivative at x minus the antiderivative at a. So the integral from a to b of f of x dx is equal to the antiderivative at x minus the antiderivative at a. So let's look at y equals x squared. Find the area under the curve from x equals 1 to x equals 2. All right, so we want to find the integral from 1 to 2 of x squared dx. So we want to use the power rule for integrals or antiderivatives. And so that means we are going to go up 1 degree. So 2 will become 3. and then we will multiply by 1 over that new exponent. So since we're going to have a 3 here, we're going to multiply by 1/3. Because if we took the derivative of this and worked the other direction, you would do 3 times 1/3 to get you your 1, and you would take 3 down to 2. All right. So we're going to go from A to B. So we plug in the B value first. So it's 1/3 times 2 to the third. And then we subtract the function evaluated at the A value. So 1/3 times 1, because 1 cubed is just 1. And so we get 8/3 minus 1/3. So graphically, what's going on is 8/3 is the area under the curve from x equals 0 to x equals 2. Okay, so it's more than what we need. It's the entire area under this curve. So we need to subtract off what we don't need, which is the area from x equals 0 to x equals 1. Okay, so we get 8/3, that's the whole area. Then we subtract off the 1/3 that we don't want, and we get 7/3. And 7/3 is the area under the curve from x equals 1 to 2. So what we're using is the reverse power rule. The antiderivative of x to the n is going to be x to the n plus 1 divided by n plus 1. Or you can do 1 over n plus 1 times x to the n plus 1. And then we have to indicate that you could add any constant you want. So plus c, where n is not equal to -1. All right, the antiderivative of x squared is 1 over n plus 1, so 1/3 times x to the third power plus c. If you wanted to write this as x cubed over 3, where it fits this exactly visually, that's great too. All right, guys, go ahead and print out your problem set and start on any problems you can. You will have a quiz at the end of class. Come by and see me if you are just completely stuck. I will see you in class, and thank you so much for watching the video.